Welcome to CS 101, Scientific Python, Lecture 18, on solving equations. Today, we're interested in considering what happens when we actually solve equations on a computer. There's different kinds of things that we have to worry about when representing equations and worrying about what this means. Previously in Python, we've worried about writing expressions. And when we've talked about solving things, we've normally either meant applying SymPy to find an analytical solution, or we've meant it in a generic sense as in solve this problem, solve this homework assignment that's been given to you. We're going to learn about how to measure how long a program takes, and this gives us a way to start to talk about program efficiency. And then finally, we're going to start learning how to locate salient functional features. When we write down an equation, we're often interested in things like minima or maxima, or solutions, crossings, zeros. Suppose that we wish to evaluate a particular function. On a computer, we have to start worrying about what kind of implementation is the right way to do this. So mathematically, we would write this equation as y equals a sine cubed x plus b sine squared x plus c sine x plus d. On a computer, we can write this in one of two ways. Option 1 involves using sine x explicitly as we calculate y as a function of x. Option 2 calculates an intermediate variable t and then uses t in defining y. Now, most of us would prefer option 1 on aesthetic grounds. The equation that we've written for y looks like what the actual mathematical statement should be. However, the first way takes 3 times longer on a computer. Each time the function sine is used, it is calculated again. Sine x is calculated again. Whereas in option 2, sine x is calculated once, and the value resulting from that function call is used over and over again, which is much more efficient. Generally speaking, you should avoid multiple unnecessary calls to a function. This means that sometimes solving a function in 2 lines or more is better because it takes less total time to evaluate in Python. In mathematics, we often talk about special functions. This means things like sines, cosines, logarithms, factorials, exponentials, and other relationships which we use to conceal underlying complexity. For instance, an exponential is actually defined by an infinite series, defined as x to the I over I factorial as a summation. However, it's inconvenient for us to recalculate this as a series every single time we need to do it. So we talk about just using exp, or e to the x, to calculate that value for us. If we wanted to use this on a machine, we would either write the completely equivalent expression e to the x, where e has the value 2.71828, etc., or we could compute some version of this infinite summation above, or maybe we get lucky and there are some numerical tricks that we can use. In practice, the summations used for special functions tend to converge fairly quickly, and this makes an iterative process feasible. It's more convenient and less error-prone to define a function like exp and use it consistently. If we try calculating e to the 2, or exponent of 2, term by term, we can fill out a table which includes the term numbers, the expression for that term, the numerical value of that term, the sum of terms up to and including this term, which means the finite approximate value that we have at this current step, and then the residual error that's left over in calculating this value. So you'll notice as we look down each row in this, that with one term, we have a lot of error, 6.3891 values. As we add each subsequent term in the series, our error goes down fairly quickly. And by the time we get to 9 terms, we're accurate to 4 significant figures. Some methods will be faster, some will be slower. And the selection of a particular series is part of the critical choice made by the numericist in carrying out these calculations. Here we've defined a series exponential, which calculates each term inside of this while block. N in this case does not mean the number of terms, it means the number of significant figures that we're requesting to be available after the decimal point, thus this 10 to the negative n quantity. And at that point you break out of the loop and you return your result. Let's see how this behaves. So we'll give it 2, just like we saw on the table a moment ago. And let's calculate to, say, 8 significant figures of accuracy. And watch how long this takes to run. It runs pretty quickly to get to 8 significant figures. Let's go to 12. Also pretty fast. 16. We can't really go beyond this because a floating point number doesn't have any more accuracy than this. And you'll notice that when we ran these, there was a slight delay, but it wasn't something that even a human with a stopwatch would be able to measure. However, things like the series solution that you're using really affect the efficiency of your overall calculation. So we're going to talk briefly about how we time code and some of the ramifications of choosing one method over another. If you're interested in the details behind these sorts of calculations, you should consider taking CS 357, CS 450, TAM 470, or the TAM 541-542 series someday, as these courses examine numerical methods for calculating functions and solving equations.